Thanks very much, Christopher. So as Christopher said, I'm here on behalf of the Institute of Physics and in particular the Gravitational Physics group of the Institute of Physics to present our speaker for the Gravitational Physics Group Thesis Prize 2021. So the Institute of Physics, for those who don't know, is the professional body in the UK and Ireland for physicists and for physics. If you're not a member, I'd encourage you to join. And when you do join, I'd encourage you to join the Gravitational Physics Group, which you'll be able to do for free after you've joined the IOP. For graduates, as I imagine most students attending this meeting will be, there's heavily discounted membership of the IOP in the first few years after you've graduated. So one of the things that the IOP Gravitational Physics Group does is present the Thesis Prize. So this is the annual group Thesis Prize for members of the IOP who've passed their Viva Voce exam for their PhD within the previous 12 months. There's a specified time frame. So there's a nice prize of £500, an invitation to submit an article to Classical and Quantum Gravity, the IOP journal, and an invitation to present your work at the annual BritGrav meeting. So the 2022 competition, there'll be an announcement later on in the year. Please watch out for that. And you can see the link there to more information about the Thesis Prize. So our winner this year is Dr. Fabian Gittins. Congratulations to Fabian of Southampton University for his thesis entitled Gravitational Waves from Deformed Neutron Stars, Mountains and Tides. So Fabian is going to present a talk based on his thesis in a moment or two. You can just see the quote there from one of the judges for the prize, Matt Pitkin from Lancaster, who has commented that this is a highly comprehensive thesis that represents a large body of published work that also provided an excellent critical analysis of previous work and how it built and improved on that. As chair of the Gravitational Physics Group, I want to thank very much the judging panel who had a number of PhD theses to read and to make their assessment of as part of this prize process. So that's Dr. Juna Kroom from Durham, Tim Clifton from Queen Mary, Scott Melville from Cambridge, Chris Moore from Birmingham, Matt Pitkin from Lancaster, and David Tang from Bath. Not mentioned here is the person who actually did all the work in coordinating the thesis prize, and that's Patricia Schmidt. And really, I'm here on Patricia's behalf. So Patricia is the secretary of the Gravitational Physics Group. She did all of the legwork, getting everything organized and coordinated. So big thanks to Patricia and to our colleagues who carried out the judging process. Okay, so I'll stop yapping now and hand over to Fabian. If you could share your screen now, Fabian, and take it away for your talk. Thanks very much.
Thanks, Brian. I'll share my screen now. Great. Hopefully this works like it did in the practice. Thank you, Brian. Thank you to the organisers for putting on a very exciting BritGrav. There's been a great variety of talks across these past couple of days, and I think everyone who's spoken has done a fantastic job. Thank you so much to the Gravitational Physics Group and the panel that have awarded me this thesis prize. I'm going to do my best to summarise some of the main ideas that were in my thesis. For those of you that would be interested in looking at some of the technical details, I did put it on the archive back in September, and that should contain all the extra niggly bits that won't be covered in this talk. So let's make a start. So I think this is a kind of a natural point to start with any talk when it comes to gravitational waves. I think we really do live in a very fortunate period of time when it comes to gravitational wave astronomy and astronomy more broadly. Since 2015, the first binary black hole merger, GW 150914, I was in the middle of my undergraduate degree in Birmingham, and I remember the absolute raucous sort of cacophony of excitement that came about from that detection, and those of us that are interested in astrophysics. Since then, we've really got a large catalogue of detections, all of them so far compact binary coalescences. And those of us that are interested in neutron stars, we've had a reasonable slice of the pie. Since 2015, well, since 2017, actually, we've seen 2 neutron star binaries and 3 neutron star black hole binary candidates as well. And this picture here, I think, sort of tells it all. Broadly speaking, at the moment, the way in which we're classifying neutron stars in these detections is we look for objects that have a component mass of roughly about 2 solar masses or less. So there's a system here that obviously is a bit fringe, you can imagine. And this is broadly comes down to the idea of neutron stars having a maximum mass. When the neutron star is sufficiently large, it will no longer be stable to radial perturbations and will collapse to a black hole. And this is an interesting open question, but these are how we see these systems. There are probably broadly 3 configurations through which neutron stars can radiate gravitational waves. Those include the compact binaries that we've seen, where the tidal field of its partner will play a role in deforming the star in the inspiral. There are also neutron stars that are rapidly spinning. We see this using our EM telescopes, and if these objects are host deformations that are non-axially symmetric with respect to the rotation axis, this in turn provides a quadrupole moment through which these objects could generate gravitational waves. And also some of us are also quite interested in the natural modes of oscillations that neutron stars will possess, and potentially their corresponding instabilities, such as the CFS instability, which has been of interest since the 1970s. We have yet to see either of these 2 systems, those with mountains or those with oscillations, but that hasn't stopped us trying. The first detection, as I alluded to, came back in 2017 with this incredible multi-messenger event, GW170817. What made this system special, other than the fact it was a set of binary neutron stars, was the fact that we also saw electromagnetic counterpart signals. So here on the right shows you kind of a summary of the detection. So shortly after the gravitational wave hit our detectors, about 2 seconds later, there was a gamma ray burst which was picked up on. And then because of this electromagnetic associated signal, we were able to actually reasonably well localize this source and watch it over several weeks and months and be able to observe the sort of kilonova that came with it. And this was an incredible event for many, many reasons, but I think mainly because it married this traditional way of doing astronomy using our electromagnetic telescopes alongside gravitational wave astronomy, which I think is here to stay. One of the reasons we're interested, say in my group here in Southampton, but also all across the neutron star community, the reason we're interested in neutron stars is partly because they are such exceptional objects. They possess strong magnetic fields, potentially some superfluidity. There's lots of glitch behavior that many observers are interested in understanding. But I think one of the main reasons we all write on our proposals for research is looking at the ultra-dense nuclear matter equation state, and gravitational waves will hopefully help us to be able to probe that. And like I've said, although there's been no confirmed detections of isolated systems, we've only seen binaries so far, that's not entirely unuseful information to us. We know the sensitivity of our detectors, and so therefore that gives us upper limits of how large these deformations must be. And there's lots of people doing some really hard work on that in the continuous waves groups. Let's take a step back a bit and ask ourselves the question, why should one expect or perhaps motivate why we should look for gravitational waves from neutron stars, rotating neutron stars? And actually, these have been interesting objects well before LIGO came into the picture. Since probably the 70s and 80s, low mass X-ray binaries, so those are systems where there's a compact object, so a black hole or a neutron star, a bit like this this cartoon here on the right, that is getting matter from a neighboring star, so like a low mass star, so maybe smaller than our sun. And as this matter falls to the neutron star or the black hole, it'll form some circumstellar accretion disk because of its angular momentum. And then as the matter then falls from that disk onto the poles of the neutron star, we see the X-ray pulsations. And so these are well-observed systems. And they're quite natural sources for gravitational waves for two reasons. One is if the matter piles up in some sort of non-axisymmetric manner, right? So the neutron star will have a rotation axis. If its poles are misaligned with the rotation axis, which is what we observe because we see them pulsate in the X-rays and the radio waves, then the matter will probably fall onto the poles because of the magnetized nature of it, and that will potentially create some sort of mountain or bulges. Also, there's temperature asymmetries associated with these accretion episodes, and that could play a role in the stars entering the R-mode instability window, for example. However, we've noticed for as long as we've been able to see these systems that none of them have been able to spin up the neutron stars very fast. Well, what do I mean by that? Well, as the angular momentum hits the star coming from the companion, that will transfer angular momentum and spin the star up faster and faster. And in principle, things like magnetic fields and some sort of accretion magnetic field torques probably won't be large enough to halt the spin down or halt the spin up of these objects. And so we would imagine we'd be able to spin these objects up until about the sort of centrifugal breakup frequency at which matter starts to get thrown off the star. But that's not actually what we observe. Actually, what we observe is shown here on the left plot here. These are about the 30 or so systems we've seen over the past 20 or so years that we've been looking at these objects. And what I'd like to draw your attention to is the fact that there exists a really sharp peak towards the higher frequencies of this plot. Nothing spins even remotely close to the centrifugal breakup frequency, which will be about 1 kilohertz, maybe 1.5, depending on the equation of state. And so this suggests, this peak included, suggests that there probably is a mechanism acting on these systems that is taking away angular momentum from the neutron star. Now, gravitational waves are very natural because gravitational waves carry themselves energy and angular momentum. And so we looked at this a few years back. We developed a simple population synthesis model for the spin evolution of accreting neutron stars. We included things like the accretion rates, the magnetic fields of the stars. We also had some phenomenological models for the coupling between the accretion disk and the magnetic field. As the field lines will thread through that will take away angular momentum from the star. And we also modeled persistent and transient accretion episodes for these objects. What we found is if we did, even with like a fairly sophisticated treatment with some of these aspects, like this coupling I'm describing, if there was no angular momentum in the system, then actually these systems were able to spin up to the centrifugal breakup frequencies, no problem. And you certainly did not get the characteristic behavior of the histogram I showed you on the previous slide. However, the moment you include emitted gravitational waves, whether that's through something simple like you assign a quadrupole moment, or you come up with maybe a more interesting model for transient accretion and thermal mountains that are induced that way, then actually you obtain qualitatively similar distributions of the observations. And that's shown here in the plot in the bottom left here. In orange, that's the observed population of stars that we see in our sky, and in blue is what we simulated. And what is particularly interesting is that we regain this sort of, it's not quite as sharp as what is observed, but we regain a peak towards the higher frequencies, and none of our systems are able to spin up to breakup frequency, which is interesting. And a natural direction that one might want to take work like this is they might want to connect the accreting population that we see with the rapidly rotating pulsars that we've seen far more of, since these are the systems, these are the incubators that are going to create our rapidly rotating radio pulsars that we see. And it's possible that gravitational wave emission could play a role in that story. And we certainly don't see any radio pulsars that spin as fast as the breakup limit. So now hopefully I've convinced you that gravitational waves, well, hopefully I've made a case that gravitational waves can play an important role in the life of a rotating neutron star. Another direction we had a look at, which has been a theoretical question that has been asked for about 2 decades, is how large can a deformation be on the neutron star before its crust, the solid elastic crust towards the surface of the star, before that breaks, since that will provide your upper limit. And this is a nice limit to compare and contrast with the upper limits we're currently getting from gravitational wave searches for these systems in the data right now. Previously, approaches tended to follow this very nice work by Gregor Chemirsky back in the year 2000 for his PhD thesis, where Greg adopted an approach where he ensured that the crust in a sort of very much a theoretical way was strained at every single point to its maximum strain, such that if it was strained slightly more, the crust would fracture. However, it doesn't seem that such a technique respects the boundary conditions of the problem. In particular, you need to worry when building a neutron star, well, a stellar model with some elastic component, that you respect things called the traction conditions, which are the stresses across the fluid elastic boundaries from the core to the crust. So we had a look at this problem and tried to formulate a way of solving this while fully respecting the boundary conditions. On the left here is how one typically understands the mountain calculation. So you imagine you have a star, star A, which is a new young neutron star that, say, is rapidly rotating because it has some angular momentum from its progenitor. It's hot, so it doesn't have a crust yet. It's a fluid object, and it has a shape that looks like this. Now, in reality, we tend to do these calculations perturbatively. So we've got a reference star here, S here, which we know how to build, and we'll build A as a perturbation on top of it. Then we imagine that our star A starts to cool down, it starts to slow down its rotation and relaxes into a shape of A tilde. Now, as it's cooled down, a crust will develop towards the surface and it will look much more like one of the older neutron stars that we expect. And then we imagine that as it spins down, it changes its shape again because there's no centrifugal force to hold up the star. And we get something like star B. And because it had an elastic crust that was relaxed in the rotating, in its previously rotating configuration, slowing it down will change its shape and will build up strains in the crust. And that can break. And that's quite similar to how a lot of people think about the glitch problem as well. Now, B is the star with the mountain that we care about, and we want to understand how big can the mountain be on star B. Now, it turns out that the left-hand approach, while true physically and a useful tool to understand the problem, you kind of mask the force in the calculation. So what we did is we included the force, the evolutionary force which sourced the mountain, and we had a scheme that looked like what I'm showing here on the right. So we introduced 2 new stars, S tilde here, which is a spherical relaxed star with a crust, and then we applied the same force, so like say centrifugal rotation as an example, to star S tilde, and we get star C, which is a neutron star with elastic crust that is strained. And then you can subtract stars A and C from one another, and to linear perturbative order, one can obtain star B. This is shown perhaps more in detail in the papers, but I think it's an important point to note. And what's useful about this technique is one has full control of the boundary conditions, so one can satisfy the traction conditions, and also one explicitly puts in this ingredient, this applied force. And that's kind of important, and it's natural that one should expect this applied force should play a role in how large these mountains can be. So we did this calculation in full general relativity using a realistic nuclear matter equation of state, and we deformed our neutron stars subject to a few specific deforming forces, and these forces were mathematical in nature rather than being connected with the exact physics of the formation history of the star. Since that's a calculation we think will probably require a lot more work. And then what we did is we ramped up the amplitude of each force until the crust began to fracture at a point, and this gave us the maximum mountain that each star could support for a given force. On the bottom left, I'm showing you is a plot from our work. The different coloured lines correspond to the different deforming forces we considered, and you can see just over some simple different mathematical forces that actually the quadrupole moment, which is what's plotted on the vertical axis, can differ by several orders of magnitude. And that's quite natural because the force is connected to the formation history of the star, and depending on what different evolutionary processes the crust went through will affect its shape. We also considered the role of the equation of state in supporting the mountain. So we focused on one specific force, and we implemented a subset of equations of state obtained from chiral effective field theory. All these equations of state obeyed things like thermodynamic stability and causality for the speed of sound throughout the star. And on the right, you can see the different equation of states that we considered, and people tend to parameterize equation of state in terms of the mass radius diagrams they draw out for neutron stars. And in the shaded region, I'm showing the sort of equation of state that satisfy current observational constraints. The dashed line corresponds to two solar masses, since there is reasonably strong observational evidence that the true nuclear equation of state must be able to support neutron stars of at least two solar masses. And then the other two lines correspond to results from the NICER experiment, which give us bounds on the mass, on the radii for a couple of different stars, neutron stars. On the left, we're translating that sort of allowed region to the quadrupole moment plot. And again, you can see that the narrative is quite similar, which is the equation of state actually plays quite a big role in how large these mountains can be, depending on which equation of state you allow within this sort of equation of state that satisfy the observational constraints. You get about an order of magnitude. Now this is quite an interesting but rather technical calculation. We very much feel like we've only scraped the surface. In reality, it seems to us that actually the real open question here is, how does one connect the sort of scheme I showed you with the forces with the actual evolutionary history of a neutron star, take into account things like spin down, things like crust fracture, things like accretion episodes and the magnetic field playing a role in shaping the crust. All of those seem like really important questions in order to connect and actually give people sensible mountain sizes. Another thing that is worth commenting on is we considered our neutron star crust to be a pure elastic solid. So you know, from hopefully elementary school, we can all remember the Young's modulus, which is the proportionality constant between the shear stress and the strain that's applied to a solid, and a perfect elastic has a straight line for that. Now, in reality, we know from most materials on Earth that many solids, in fact, most solids, exhibit some degree of plasticity, which means that you can go beyond the elastic limit, and the solid will hold on to some of the strain, even though you might have to be stressing it a little bit more before it completely fractures. And that's kind of an important point, because if a neutron star crust has some degree of plasticity, one could imagine that you could strain the crust up until its breaking strain, its classical elastic yield limit, and then strain it some more at different points, which enables the crust to maybe achieve a larger quadrupole moment. So it certainly seems worth noting and following up on. We also went on to then consider a problem that is well trodden by now, which is tidal deformations on neutron stars. I'll do a whistle-stop tour of this one. Neutron stars are different to those of black hole. Neutron star binaries, their waveforms are different to those of binary black holes, owing to the fact that the neutron stars themselves are not vacuum, they are material bodies that can be deformed by the tidal field. And those deformations will result in the neutron stars in spiraling faster due to the friction and dissipation that occurs in those deformations. And that's what I'm showing you in this little cartoon of the gravitational waveform. And those finite size effects are really quite important for us getting a handle on the neutron star equation of state. And that's what I'm showing you here on the left. This is one of those famous plots from GW 17817, which shows you the two tidal deformabilities of the component stars. And although we didn't actually see the tidal deformability in the gravitational wave signal for GW 17817, and we haven't done so far for the other systems, that isn't useless information, because that tells us that the tidal deformability must be below some upper limit. And that's what these lines tell us. And the hope is that with more detections, and hopefully with maybe a closer binary and hopefully an actual detection of the finite size effects, we'll be able to wrap around the true neutron star equation of state. We considered the role of the elastic crust in such deformations because we were simply set up to do so. And unfortunately, it's a rather disappointing story, which it turns out to be, which is that actually whatever physics you add to these neutron star models, we can't seem to be able to see it, which upsets me and my collaborators to no end. Here on the right, I'm showing you the tidal deformabilities for a neutron star with a crust versus one that is the exact same but without. And you can see from the numbers on the vertical axis that these differences are ordered 10 to the minus 5%. So utterly tiny, unfortunately. And this is certainly beyond what we have with our current generation gravitational wave instruments, and very likely beyond third generation as well. We also had a look at the question of when the crust might fracture during an in-spiral. And this, we looked at a very simple 1.4 solar mass component system and calculate the crustal strain throughout an in-spiral. And we found actually that the crust was surprisingly robust during the in-spiral. And on the right, I'm showing you is the gravitational wave frequency at which that point in the crust broke. And you can see actually the vast majority of the crust actually survives. It's only that sort of very, very thin layer at the outer crust towards the surface of the star and neutron drip, which is a phase transition. So I think a future direction for some of this work would be maybe to look at things like magnetic fields. I think that's another thing to maybe see whether that kind of physics. I think already people have tried to understand whether superfluidity makes a difference in these in the tidal deformability as well. Right, I think I'm probably running a bit afoul of time. I'm getting the head nod from Christopher, so I'll wrap up now. So I hope I've convinced you that there are good reasons to expect gravitational waves to play an important role in the dynamics of neutron stars. We certainly there is observational evidence for that from the electromagnetic data from the spin distributions of accreting neutron stars, and that we were able to show with a simple population synthesis study that these can be explained using gravitational wave torques. The question of how large a deformation the crust can sustain is inevitably going to require us to get to real grips with the formation histories of these stars, and I'm afraid that probably won't happen anytime soon. Neutron stars are extraordinarily complicated objects, and there are many open questions with regards to them. But there have been some evolutionary calculations done in the past, and it'd be interesting to see more of those to maybe make progress on this problem. Neutron stars that exist in compact binaries are well known and perhaps well celebrated gravitational wave sources, deservedly so. We found the crust was surprisingly robust during the in-spiral, but it leaves perhaps an almost impossibly small signature on the waveform beyond our ability to detect. There are plenty of interesting science questions to remain, and I think it's an exciting time for those of us that work on neutron stars and are interested in gravitational waves. Thank you so much for your attention.
Cool. Thank you so much, Fabian, for such a comprehensive talk. Do we have any questions for Fabian? Yeah, one from Greg straight away. For the detectability of crustal effects is it possible to determine the gravitational frequency at which it is observable? Could, for example, a 3G detector with better high frequency sensitivity improve the detectability?
Yeah, that's a great question, Greg. I don't know. All I know, I think Nils and I, to be honest, just looked at these numbers and they're just so beyond anything that's been quoted for ET at the moment. Obviously, a question a lot of I know people are thinking about with this Australian detector, I think NEMO, which might be more set up for neutron stars, is about tuning your strain curve such that it has the right sensitivity for the objects you're interested in. I don't think so, but I would love to be proven wrong about that, Greg.
Cool. Okay. Any more questions? I had one, which is you outlined the different ways of detecting gravitational waves from neutron stars. And so obviously we have the compact binary coalescence already. Do you have a feeling about which would be the next for us to detect?
Out of the three I listed? Yeah. Do I have... I don't think I can really know, because I think there's such varied physics. Obviously, I'd love to see something from the mountains. I think there's some really excellent work going on from continuous wave groups all across the world at mining the gravitational wave data and improving their algorithms in order to look for these very small signatures. But I'm also, ashamedly perhaps, optimistic about looking for unstable modes as well. Yeah, I don't know. I think either one of those are possible. I think actually third generation will hopefully help us get closer and closer to the sensitivities we need.